Hello, everyone, and welcome to our fourth edition of eMissions Talks webinar series hosted by Process Ecology. I'm Sophia Alva, your host for today. Today, we'll be talking about tuning process simulation models to match plant data and what are some of the key insights and best practices. Accurate process simulation is critical for optimizing performance, reducing costs, and meeting production targets in the oil and gas industry. From gas processing plants to refineries, distillation columns are essential for separation and purification. Yet they are also one of the most complex units to model and tune effectively. Process simulation tools like Aspen HYSYS, Unisim, and others are widely used across the industry for everything from equipment design and debottlenecking to energy efficiency studies and operational troubleshooting. But the reality is that even the most sophisticated simulations are only as good as the inputs and assumptions they're built on. One of the most common areas where models start to diverge from reality is the modeling of distillation columns. These units are at the heart of gas plants and refineries, and yet tuning them correctly remains a challenge. Efficiency models, particularly the differences between Murphree tray efficiency and overall efficiency, can be confusing. And if applied incorrectly, they can skew predictions and separation performance, energy requirements, and product quality. A poorly tuned model can result in costly decisions. You might over-design equipment, miscalculate product yields, or miss the opportunity to improve energy performance. On the flip side, a well-tuned model provides clarity. It helps you test scenarios, predict plant behavior under changing conditions, and make confident recommendations to operations and management. In this webinar, we'll talk about what tuning actually involves, the most common pitfalls to avoid, and how to use efficiency models correctly. Our goal is to help you get more out of your simulation tools and ultimately bring your models closer to the reality of your plant. Joining us today, we have Denis Westphalen, Process Ecology's Senior Technical Engineering Advisor. Denis has over 30 years of work experience in process engineering, including process design and optimization, operations support and troubleshooting. He is an expert on building simulation models and on the use of pinch analysis for heat integration. Lately, his focus has been on energy efficiency and GHG emissions quantification, forecasting, and mitigation. Hi, Denis. We also have Chahad Agarwal, our process engineer and R&D analyst. Chahad has 5 years of experience. 5 years of experience as an R&D process analyst. He brings a strong research background combined with advanced process simulation skills to drive innovation in process modeling. His work spans a range of areas, including gas processing, crude distillation units, flare systems, GHG emissions, and carbon capture. Hi, Chahad. So now Denis and Chahad will go over their insights. So please feel free to submit your questions in the Q&A box available throughout their presentation, and we will get to these questions at the end. So we'll just share the screen now.
Okay, ready to roll? Okay, so good morning or good afternoon, everyone. Nice to see some familiar names on the audience. So the goal here is to give you guys a highlight, a quick overview on the challenges that we face when tuning simulation models with focus on distillation columns. That's kind of a little bit of our bread and butter here at Process Ecology. And before I kind of jump into the slides, let me share a little bit of our motivation in putting together this webinar. Uh, so here at Process Ecology, most of the work we did is with the existing plants. So we are not an engineering design house. We typically help operators around the world. And so what happens is we are not really designing equipment. We are typically working with existing plants. And when we build the simulation models, or sometimes as big buzzword where we build these digital twins, we have to make sure that our simulation models, either in HYSYS, Unisim Design, or any other simulation tool, we have to ensure that they match what the plant is doing. Now, some of you might think that that's not the case. Isn't that the default when you're using a process simulator? Well, the reality is, no, it's not the default. So to make sure that your simulation model matches what the plant is doing, we have to go through this step, what is called tuning. And so tuning is applied in different areas of a process. But in this particular webinar, we are going to focus on distillation columns, which is, in our opinion, the most tricky part of your process, that it has to be tuned. And well, if there's interest out there, we can extend and plan another webinar on other pieces of equipment. But on this particular webinar, we're going to focus on distillation columns. Okay, so understanding tuning. Why do we have to tune? So how come when I started building my model, it is not tuned right off the bat? Well, the key challenge here, the key point is, as on the slide there, so the process simulators, they assume equilibrium conditions. So you have a separator, we have a vapor phase, a liquid phase. So the simulator will assume that that vapor leaving the vessel is always in equilibrium with the liquid leaving the vessel. That's not what happens in our real plant. So usually you don't have enough residence time so that the phases meet equilibrium conditions, or you have other imperfections in your process, such as fouling, certain heat exchangers, or in the case of distillation, we have inefficient trays, or we have heat losses. So there are many factors that may impact the performance of the plant, which means that whatever your simulation is saying will never match exactly how the real plant behaves. So then, what is the role of the tuning factor? Is to close that gap between the ideal model and the actual plant performance. Well, and we have to make sure that we build accurate models. Otherwise, those models are kind of useless, right? So they don't do anything if we cannot match plant performance. Okay, so a very important concept we have to discuss is the difference between a design model and a rating model. So we have a slide with that. So a design model, so it's a simulation model where typically we specify outlet conditions. So for example, you have a heat exchanger, you specify the outlet temperature. And uh, all other parameters that are calculated. So this type of model is typically used when you are in the design stage of a new facility. So you have a new facility that has to be built. So these are the process conditions. And hey, someone at some point is going to design an equipment that will match that required process condition, right? But at the initial design stage, I don't know the specifics of that equipment. I don't know what it's going to look like. I remember a long time ago, I was helping an engineering small company. They were working on a refrigeration plant, and then I noticed that there was a heat exchanger, that there was a temperature cross, right? Which is, we know from a process point of view, that's impossible. But the thing is, the process simulator takes it. Okay, so if you want to cross temperatures, which isn't feasible from the thermodynamics point of view, from the heat transfer point of view, you cannot design that equipment. So I kind of inquire, so aren't you going to fix that? Oh no, the mechanical engineer, when he designed the exchanger, he will deal with that. He's going to fix that. No, 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 right? So that's the problem of building simulation models when we're just restricted to design mode, kind of set outlet conditions and just hope for the best that you're going to have an equipment that will give you those outlet conditions. Now, on the other side of the coin, we have a rating model. So what is a rating model? A rating model, typically, we define some performance parameter of the equipment, and the simulator is going to tell you what the expected outlet conditions are. So it's kind of a going the other way around, right? So we use that model to match real plant behavior, and we calculate process outlet conditions instead of specifying those. And well, of course, for a given plant, that's a more accurate simulation. And even at design stage, I mean, I do hope that uh, people here on the call that work on the design kind of environment, I do hope that at the end of the design, you flip that model around on a rating mode to make sure that you can meet the specified process conditions, right? So have a slide here with an example, kind of a as a picture example. So on the left here, I let's say that I'm building a model on design mode, and I will have a kind of a color code there, a legend, red for specified values and blue for calculated values. So for example, I specify my inlet conditions, PT, pressure, temperature, flow, composition, and then I specify the outlet pressure of the pump. Then I specify the delta P of the valve. So the simulator is going to calculate the pressure and the CV of the valve. Then on the heat exchanger, so we specify the inlet conditions of the other side of the exchanger, and then the simulator is going to calculate, we specify T and delta T of that exchanger, and the simulator is going to calculate the duty, UA factor, so on and so forth, right? So we typically specify mostly outlet conditions, and the software will give you an approximation of the equipment that will be required to meet those conditions. Now, on the rating mode, so how would that work? So let's go again. So starting with the feed conditions, so PT, flow, and composition. For the pump, typically, instead of specifying the outlet pressure, we will provide a pump curve. So we know what that pump looks like, have a pump curve from the vendor, etc. And based on that flow versus head relationship, the software will give you what the outlet pressure of the pump is. Then comes to the valve. So then we specify the CV of that valve, and based on that flow and that CV, the software is going to calculate what the delta P is and the outlet pressure. Or if you want to go fancier, you can play with the variables and you have that flow calculated as well. All depends on how the variables are configured. Comes to the heat exchanger. So let's say that one side, on the other side, we have the inlet conditions known. Then our specification is not the outlet temperature, but rather the UA factor Or sometimes we go further and go all the way to a rigorous calculation, so we can embed an EDR, Aspen EDR, or the HTI. So when you have access to those engines, so you can run the rigorous thermohydraulic calculations for the exchanger, and then you would get the outlet conditions specified. So here at Process Ecology, we had the opportunity of building uh, models for preheat trains of entire crude distillation units, where every single exchanger we specified, we model using a rigorous calculation, and then we could do lots of studies around that preheat train, imposing different fouling factors, taking plant data to regress, do some statistical analysis on those fouling factors, so get a very, very accurate simulation of that existing plant. Okay, so typical tuning factors. So varies depending on the equipment. So in distillation columns, which is going to be the focus here, we are going to talk about efficiencies, heat exchangers. We work typically with UA factors, fouling factors, rotating equipment. We have performance curves and things like that. And so by doing model tuning, we kind of build a model that takes into account the real constraints and performance of the plant to predict what the plant can do. Okay, so with that introduction, now I will pass to Shahat, who is going to go on a deep dive to distillation column. So Shahat, carry on.
Thanks, Dennis. Now we'll bring our focus back to distillation columns. This slide will summarize why efficiency modeling is so critical when tuning a distillation column in process simulators. First off, because distillation is driven by vapor-liquid equilibrium, columns are inherently sensitive to even small deviations in performance. So let's say slight changes in tree efficiency can have like large ripple effects on separation, product purity, and operating costs. Second, the relationship between efficiency and column behavior is not linear. A drop in efficiency or a different efficiency model, it just doesn't affect purity of the product, but it also can significantly affect the column running. For example, the energy consumption, the required flux rates, your duties for the reboiler, etc. That's why it is essential that the efficiency model selected in your model reflects both the column's actual mechanical design and plant operational data. Using a generic or guessed just a generic efficiency value or a efficiency type can deeply throw off the predictions. Um, there also can be mismatch of how efficiency is modeled, and we have seen numerous technical articles from reputed sources which mix up the model. So we want to explore this further in our next few slides with a real world case study comparison. Okay, so let's clarify the two types of efficiencies we are comparing. First of all, we have overall efficiency, which is applied at a column level. So how it works is that for process simulator, you enter the number of theoretical stages, which corresponds to the overall efficiency number. So for example, you want to implement an 80% overall efficiency and you have 10 trays in your column. So theoretical trays becomes 10 into 0.8, that is 8 number of trays in your simulation model. Secondly, we have tray efficiency, or also called Murphree tray efficiency, which is applied tray by tray. For building this model, we keep the actual number of trays similar to the plant, and we specify a vapor liquid efficiency number per stage. Notably, the efficiency per tray can be different at each stage, and you can also group together some trays and specify a number for different groups. That is also possible for Murphree tray efficiency. Uh, There's also the talk about vapor liquid equilibrium. So when you are implementing overall efficiency, so all your trays are at equilibrium. All the vapor and liquid equilibrium leaving each tray will be at equilibrium for overall efficiency model. But for Murphree tray efficiency, we are disturbing that phase equilibrium for each of that trays. Um, so going to the next slide, we'll have a great visual example. On the left, you can see that there's an actual plant column configuration. We have kept the number of trays to be 10 for demonstration. In the middle, we have the simulation model, which indicates the overall efficiency model. Here you can see that we have assumed 80% efficiency, so the number of trays become 8. The other point is that it has also affects the draw stage or the feed stage. So you can see that the feed is entering the stage number 6 on the actual column. But if you incorporate that also with the overall efficiency, the feed stage changes from 6 to 5. Um, and depending on your overall efficiency, let's say if you're working with 50% efficiency or 60% efficiency, you have to modify that feed stage. And when we have more complicated models, for example, you have a crude distillation unit where you have 3 strippers, and also there's strippers and turnaround. So there, each of those stream leaving or entering the column, they have to be modified based on the efficiency number. On the right, we have the tray efficiency model, where we maintain the full actual 10 trays equal to the actual column, and the draw feed stages, they line up with the actual tray number. So for each of those tray, we implement a tray efficiency number, which affects the vapor liquid equilibrium for each of those trays. Going to the next slide. We conducted a couple of case studies to evaluate how the choice of efficiency implementation affects the simulation model behavior. So we ran systematic studies using 2 models: the overall efficiency, which is applied to the whole column, and the Murphree tray efficiency applied tray by tray. Here you can look at a fractionator column. We picked up feeds with some operating condition and a composition defined for both the models. We kept everything constant. We have feed condition, column operating condition to isolate the impact of efficiency modeling, and the number of trays, draws, feed stages for the overall efficiency implementation will change as efficiency changes. The key parameters which we are analyzing for looking at the performance of this column is the butane or C4 concentration at the bottom. So you should see that the better the efficiency is, the lower should be the concentration in the bottom, and also the overhead vapor flow rate. So now let's look at what happens when we compare the simulation models. In this case, we have examined the fractionator and plotted the the C4 concentration in bottom and the overhead vapor flow rate. We could see that as the efficiency is getting better for both the models, we see the similar trend for both of these models. The C4 concentration is decreasing with increasing efficiency, which shows better separation between the two products which we are splitting, and also the vapor flow rate. The overhead vapor flow rate, it also gets better when you have better efficiency. The key thing actually which we wanted to take out from the simulation is that we are not advocating for one model over another. We are not saying that, oh, look, see that trade efficiency is more linear, or the overall efficiency gets flattened. So so this is better, that is better. It depends on the specific case what you are trying to model, and we just want to highlight here that these 2 models, they can't be used interchangeably. So like I said, that we have looked at we have shown various technical articles. For example, what people do is that they reduce the number of trays to implement the overall efficiency, but then they also change the tray efficiency for each of those tray. So that is double correction and you are doing it wrong. Going to the next slide, we'll look at the crude distillation unit. Here, this is a more complicated column, which you have 3 different pump arounds and 3 different strippers. We have multiple products coming here out of the column. So off gas, water, naphtha, kerosene, diesel, AGO. And typically you would like to look at the TBP trends. So let's say TBP 5% and TBP 95% boiling point for looking at the product quality. So for implementing this overall efficiency and tray efficiency, we modified the number of trays for overall efficiency and tray efficiency, we kept it same. Importantly, we made one important change here, that the top and bottom trays are always kept at 100% efficiency for tray efficiency modeling, both for the main column and the side strippers. Changing the top and bottom tray efficiency has implications, and we'll get to them later. Going to the next slide. Here you can see the naphtha, Kero, and AGO 5% TBP points and 95% TBP points, and how they vary with efficiency. Again, we can see that they have same general trend. So when you see that the efficiency is increasing, your TBP 5% is increasing, which shows better separation between the products. And on the other side, we see that TBP 95%, it is reducing. So the gap between each of the product, the cuts for these products are getting better, getting sharper. But you can see that in the between, so these two models, they don't have like a general trend that you can say that one is better than the other, similar to our message from the previous case study, that you should not use this model interchangeably and then decide based on the specific case for the plant you are trying to simulate, that which one suits better. Next, I would hand over the slides back to Denis, and he'll discuss some common pitfall mistakes and some best practices.
Okay, thank you. So few kind of comments here, advice, pitfalls, etc. Issues that we face when tuning these models. So the first one, which sounds obvious, but no, it's not that obvious. Bad input data, right? So such as the feed specs, assay characterization, or even the plant measurements. So this is something that we really struggle because when we receive plant data to run the tuning, it's very common to find numbers all over the place, mass balances that do not close, so we cannot reconcile mass balances and things like that. So that is one of the biggest challenges when tuning distillation columns against plant data is to make sure that we have a good representative snapshot of what the plant does, to make sure that meters are properly calibrated, that you have good quality data. Otherwise, garbage in, garbage out. Kind of another comments, not exactly specific to tuning, but we noticed some problems, some issues when we receive sometimes models built by other people. Well, in the process simulators like HiSys, Unisyn, Pro2, whatever, it's a trial and error calculation. There's always a convergence. And we noticed that the default numbers are too loose. And actually, we get some surprises, especially when you are going after tight composition specifications. It's very important to tighten those tolerances for both the column, the recycles in the flow sheet, because many times we run into problems just because the convergence settings were too loose. Okay, wrong mode usage. So make sure you understand the difference between design and rating. So are you adding a new heat exchanger to your preheat train? Fine, start with design because you are trying to define what the new equipment is supposed to do. But once you are kind of trying to understand the behavior of the plant, make sure you pay attention to what specs are more relevant to mimic what your real plant does. So talk a little bit about the tray efficiency. So kind of a few pieces of advice here. So first, be careful with your top and bottom tray, your overhead, your bottom. So our advice is do not mess with those trays. If you like the Murphree tray efficiency, where you enter, you input a fractional number, don't touch those trays because typically they cause issues in your simulation because of the way that the algorithm were implemented. So be careful with those like side draws. So if you specify a tray efficiency on a tray that has a liquid side draw, you're going to see some funny things on your flow sheet, like a little bit of vapor there, which might not be the case. So just be careful with those key trays on your columns if you're using the Murphree tray efficiency. Okay, and yeah, so back to that same point, kind of yeah, the flow sheet discrepancies. So we see that a little sometimes when you start playing with the Murphree tray efficiencies, when in the typical Unicene, high seas, Petrocene uh, architecture, uh, when a stream is solved inside the main flow sheet and it's exported to the main flow sheet, there might be some discrepancies in differences how that flash is calculated, uh, and those discrepancies they become more relevant if you're using a fractional efficiency for that draw tray. So just be careful with that. Okay, to finalize here, sharing our best practices, and I'm going to show a few biases here. Okay, so uh, in our experience, we are biased towards the use of the overall efficiency. So I think the key message that you should take for this entire presentation, and if you go back to those charts that Shahad presented, is that if you use an overall efficiency or the Murphree tray efficiency, the results are not exactly the same. So a column that has 80% tray efficiency is not the same thing as a column where all trays has an 80% Murphree tray efficiency. So what we find is that many people think that, oh, they are just the same. It's just a different way to enter that efficiency into the simulator. No, they are not the same. The Murphree tray efficiency, which likes very, very convenient. I don't have to mess around with the trays. I just use whatever is on my drawing. Fine, but just that's a kind of a numerical artifact to compensate for non-equilibrium conditions. But then when the simulator uses those numbers, it kind of adjusts the compositions, but then has to normalize back the compositions. So it creates sort of a non-linearities, funny solving behaviors. And the results sometimes kind of a little bit surprising. The most complicated of column is you get more weird results when you're using the Murphree tray efficiencies. And that's the reason that we kind of, as much as possible, we prefer the use of the overall efficiency. Yeah, it takes more work to set up your simulation. You have to do calculations to kind of estimate what the feed tray is, what the draw trays is, but still the simulation is more robust. The calculations work better. You don't have any funky business between the column solver and the main flow sheet. It works better. That's the bottom line, and that's our bias. Okay, so as much as possible, use the overall efficiency. Oh, and one additional piece of information: when you go to some reference books, so for example, there's a famous book by Gerald Case on modeling refinery units, and it shows a table with typical recommended tray efficiencies, right? So those tables, they are the overall efficiency, not the tray efficiency that you use, that you just input punch into the simulator. Okay, so just watch out because results are not the same. These two types of definitions do not result in the same outlet conditions for your column. That's the bottom line of this entire webinar. Okay, make sure you validate simulation with plant data. Yeah, so once you enter, test, see if you get the results. Okay, once again, avoid Murphree tree efficiencies unless necessary. Yeah, guilty, many times I used, but usually I'm not satisfied. Anyway, uh, so keep actual trade count unchanged. So go back to that's the advantage of Murphree. But if you're going to do that, make sure the top and bottom trays you use 100% efficiency for those. And okay, so that could be an entire webinar. Packet columns, right? So, whoa, but I don't have a tray. I have a packing, right? It's a completely different story. So our rule of thumb, the vendors are going to give you an HETP, the height equivalent to a theoretical plate. So use that value to calculate the number of theoretical stages, right? So, and if, of course, if the number is going to be 4.7, is your best judgment to round that to 4 or to 5. Now, the thing is, it's not a mix and match game. So we've seen many people for packet columns, they pick a number of theoretical trays. And then on top of that, they also add a Murphree efficiency. That's messy. You know, some people have this misconception that the Murphree efficiency, because it's kind of is a continuous number, right? You can specify 0.74, 0.75. So gives you this illusion that you have a continuous adjustment, correction, so it's more precise. It's not. It really is not that great. So on the big scheme of things, for that packing section, use 4 or 5 trays, and that's going to be more effective than trying to play with an additional Murphree tray efficiency. That's our experience, right? And of course, I mean, we respectively have no problem if you disagree with our best practices, but that's kind of what we have learned from our many years building these simulations models. And I think with that, we conclude our presentation. And so hopefully you guys find the discussion useful. Hopefully we are going to leave this webinar understanding that overall efficiency and tray efficiencies are not the same. If you use 80% efficiency in one case or the other case, you're going to get different results. So, and hey, overall efficiency is better.
Awesome. Thank you, Dennis and Chahad. That was very, very informative. Looks like we only have 5 minutes left, so
Sorry about
maybe I'll
that.
just ask each of you one question, if that's okay. So we'll start with Chahad. What type of data is required to tune a distillation column against actual plant operation?
Yeah, good question. So ideally, we are looking for mass balances, so flow data from the column for the relevant stream for on either mass or volume basis. We are also looking at product quality. So, for example, components, composition of key components, TPP assays, and for example, you have an A-beam contactor, so you want to get the acid gas, the CO2 H2S component, product specifications correctly. If you are looking at a crude distillation unit, then you want to get the product assays correctly. So those are important, and we are also looking at temperature profiles. So, for example, the condenser overhead and the reboiler bottoms, the temperature profiles for those, or the draws, those are all good data which help us tune the distillation column.
Awesome. Thanks, Chahad. Dennis, in your experience, is it better to tune a distillation column using one operating point or average numbers over a long period, such as hours, days, or weeks?
Okay, so that's always a question, right? So you go to your data historian, you can dump 1 year worth of data, do an average and build a model. No, no. We find that the best way is to select a snapshot that is representative to your plant. In the ideal world, you're going to plan a test run. So you're going to work his operations. So you're going to make sure that the operation is stable. You're going to set your controllers at the kind of a most stable possible situation. Let the column run for a few hours, whatever is relevant to the specifics of your process. And then you're going to collect that snapshot, that kind of a 1 year, 1 hour average, kind of make sure that the relevant samples are taken at that same time frame. And that is going to be the basis for your model. No, for tuning the model, typically we do not use long kind of a time horizon averages for tuning. That's not representative.
Thanks, Dennis. Yeah, if anybody in the audience wants to submit questions, there's a Q&A box. We will do our best to get to these questions, but if not, we can always send an email out. Dennis, Jihad, are there any questions there? If not, I can ask a question.
I don't see anything on the queue here, unless I'm looking the wrong place. People are shy.
That's all right. I can ask another question. So, Jihad, how can we validate that our simulation model is correctly tuned to plant data? Are there key performance indicators to look for?
Yeah, so we want to track the relevant variables, like I said, the product specification, key component composition. But importantly, there are also like key like acceptance criteria based for these products based on ASTM methodology. So, for example, we have D86 for distillation column, ASTM D86, which actually gives you the acceptance criteria for your specific gravity, sulfur weight percent, your paraffin aromatics, naphthalene volume percent. So ASTM has published these reproducibility methods, and you want to be close to those acceptance criteria. I
Thank
would let
you.
Dennis.
Yeah, I think we have maybe time for one more question. Dennis, how do you decide which specifications to use in a distillation column, which is supposed to match the plant data?
Oh, okay, yeah. So back to the design versus rating discussion, etc., right? So you build a column, you have a certain number of degrees of freedom, and that determines how many specifications you have to enter for the column to be solved. And one of the dilemmas is, what should I specify? The simplest answer Look at your PIN-ID, look at your control loops, and see which variables are truly controlled in your process, and that should consist the basis for your specifications in your rating model. So for example, let me give an example of a wrong one. So in a crude distillation unit, one important variable is the distillation curve of your naphtha product. No, do not specify that in your model, because in the real life, you are not continuously monitoring the distillation curve of your products, right? So typically online, you are monitoring the temperatures, the flows, and things like that, but not qualities, typically not compositions. On a design mode, yeah, everything is a fair game. On a rating mode, check on the PIN-IDs, work on a consistent manner of what the actual plant does.
Great, thanks, Dennis. Looks like we've run out of time here, but thank you, you two, for sharing your expertise with us today, and we really appreciate your time. We also wanted to mention that Denis and Jihad have written an in-depth article on this topic, which goes into more detail on the case studies. So if you're interested in learning more or want to use it as reference for future work, feel free to visit our website at processecology.com. We will be having our next webinar in the summer, so stay tuned for more information on the topic and date. Thank you, everybody, for joining us today, and we hope you have a great rest of your day. Thank you.